Okay, hello. This is the same talk, but recorded in other moments because there was a problem with the connection. So I will be talk again the same, but I hope this time you can hear to me. So thanks again to Professor Rika and all the organizations for this invitation, and I will speak about explicit solutions to different one-dimensional fractional Stefan-Like problems. The most part, okay, I have to go to mouse. The most part of this work I have been done with my advisor, Domingo Tarcia, at the Universidad Austral, Rosario, and CONICET. So, I will talk first about fractional integrals and derivative and the special functions involved in these explicit solutions. Then I will talk about the mathematical approach, which I call fractional Stefan-Like problems. Then I will talk about memory fluxes and the physical problems related. And finally, I will consider some special fractional Stefan problems. And they are explicit solutions too, of course. Okay, the definitions of a fractional integral, Riemann-Liouville derivative, and Caputo derivative are known or are known terms for you. So just look at the notation. Okay, you have we use integral alpha, Riemann-Liouville with this L, and Caputo with the C. So okay, but okay. Yes, I want the light, but I don't want it here. How can I? Ah, fantastic. Okay. Some properties of fractional and integrals derivatives as inverse operator and what happens when you first apply the Riemann-Liouville derivative and then integrate. Or sometimes if you have a special function, then the integral is a left inverse operator of the Riemann-Liouville functions. These things I will take in account when we look for explicit solutions. Also, the relation between Caputo and Caputo derivative and Riemann-Liouville derivative, as far as this relation when now they are not applied to the same function, but the Riemann-Liouville is applied to the derivative, the classical derivative to the function, or the derivative in the Lebesgue sense, because it's absolutely continuous. Well, which functions can we derive? From which functions we can compute the fractional derivatives? Of course, we have the powers. I know how to integrate the power through the beta function. I know how, and then I know how to derivative with Riemann-Liouville, and I can compute the Caputo derivative. But there are also another special functions that we know how to compute their derivative, their fractional derivatives. Look at this. We have first and second. The first is the right functions. It's a right function written in a series, and a particular case which we call the minority function, where these parameters are special parameters. Here rho is a real between 0 and 1, and it is a function who is in the kernel of the fundamental solution to the time fractional diffusion equation. By the other side, I will take, of course, the exponential of the Caputo derivative, which is the Mittag-Leffler function, and we will work also with a three-parametric Mittag-Leffler function, which is defined, of course, through a series, but their coefficients are defined in these terms, in terms of a product of gamma functions. Some special cases to keep in mind. Look that if I take a special case of the right functions, I recover the Gaussian function. Of course, this special case can be written as in terms of minority function because it is rho equals 1 over 2. Then this is the same with a different name. And if I take the special case 1 minus this right function, where now the third parameter is different, as you see, I recover the F function. And if of course, if I take the complementary, I recover the complementary F functions. Also, I can get the Gaussian with 3 parametric Mittag-Leffler functions in these terms, with these parameters, 1, 2, 1, I recover the Gaussian function for the Mittag-Leffler 3 parametric functions. So this phase, I know how to derive these special functions. Look at this. These properties are demonstrated in Pishko books, which is in Russian, but the mathematics is it's okay. So we know how to integrate this right function multiplied by a power, and so I know how to derivative, and I recover another right function in the 2 times. Look that I have put the general function here in the variable t, because I will use these results for the explicit solutions to the time fractional Stefan problems. Instead, for properties 3 and 4, which were stated by Kilbas in 1996, the integral, fractional integral, and fractional derivative of this power of the 3 Mittag-Leffler parametric function, it's again in terms, can be expressed in terms on another Mittag-Leffler 3 parametric function. That is the interesting things. And also I have choose here the spatial variable, because I will use them when I talk about the spatial explicit solutions. So come on. Okay, let's start with the mathematical approach. As I said yesterday, this is the first problem I worked with when I started my PhD. Domingo, my advisor, was an expert in moving boundary problems. So we say, let's take the most simple moving boundary problem. We say one-dimensional, one-phase moving boundary problem. And what happened if we change the fractional derivative by a Caputo derivative? So this is the mathematical model you get when you do this. But then, years later, I read the paper made by Professor Boller, where he talked about that maybe this problem could be a result of considering some special flux, some memory flux. So I said, oh, okay, that's a fantastic idea. What happens if I write the model like this? These 2 models, I say that they are fractional Stefan-Like problems, because a few years later, I realized that maybe these were not the problem derived from a physical support, but they are like them, okay? Because of that, I say Stefan-Like problems. And the point is that the derivative of Caputo and of Riemann-Liouville both started from 0 in this model. What do we know about with these models? Well, this is an explicit solution in terms of right functions of the first one for the Caputo derivative, where of course the interface is in the power of alpha over 2 of t, and there is a parameter that characterizes, which is a solution to this equation 3 that you can see here. This solution was appeared in a paper in 2009, and what we did is to our contribution was stayed in to prove that there is a unique solution to this equation. So the characterization of the interface is in this way unique. So then I said, okay, may I do the same, may I try the same strategy for the second one, the problem derived from Professor Wöhler's idea? Yes, the ideas go well, and I got again an explicit solutions in terms of right functions that are almost equal, and the interface now is again a power of t alpha over 2 with a parameter. But now the solution, this C is a solution of a different or not equation. When I was thinking about, wow, these problems are really these solutions are very similar, are the same. I think that they are the same. Trying to prove that they were the same, I arrived to the conclusion that they were different, okay? My intuition wasn't so good, but it was a very nice exercise to prove that they were different. That wasn't easy at all, and we have to study many properties of right functions, especially when the second inference is negative. That is difficult. And thanks again to Professor Sku in his book and ideas given in his book, we could prove that always the minority function is smaller than this right function, but look that if we take alpha equals 1 over 2, they are the same. So for alpha different from 1, they are different, and 1 is always bigger than the other. So we say, oh, we thought that these problems were the same, but they are not. So maybe the interesting fact is on the Stefan condition. Maybe it's not the same to consider this Stefan condition where you apply the Caputo derivative to one variable function. This is different to apply first a Riemann-Liouville derivative, which they are related, okay? But this is a function of spatial and time. First, I apply the Riemann derivative, and then I take the limit. If I could interchange the limit here, so I could have here the S of t, they could be a function of t, and then I could relate them. But the point is that I cannot interchange the limit and the derivative. So the next step was to say, okay, is this a physical model of some physical event? Well, we again following the started from Professor Wöhler, we state a problem. We say, suppose that we have a temperature with a flux, but which flux law can we consider? So it results that, of course, the Fourier law is the classical way to model the flux, but it's not the unique. You can take a kind of convolutions of flux, and this idea was pointed out in 1968, which gives us some, makes sure that this is not a bad idea, it still works. So suppose that we have an implicit flux law. I said that I will say that this is an integral from the free bound. H is the time, look here, this is the free boundary for a point x, h of x is the time where the free boundary occurs pass in that moment, okay? So I will suppose that my temperature is constant here and that the memory starts here, or for I take a point x t here, so the memory starts from here. So suppose that our assumption about the flux is that the generalized sum of background fluxes in time are at the current time, because they are evaluated at the current time, proportional to the gradient of temperature. If I do that assumption, then I will be able to say that the flux can be written in terms of Riemann-Liouville integrals. And so the model proposed by Professor Wohler is the same. But what happens when I have, in this operator, I have, it is a time derivative, integral, fractional derivative, but the starting time depends on the position. So it is more difficult to work with than when we try to work with the fractional Stefan-Like problems, when we have 0 here and we know how to derive many functions when we start from 0, but when we do not start from 0, it's not so easy. So by using the first principle of thermodynamics and Rankine-Hughes-Nacon equations, we can get a simple model of a fractional Stefan problem, a fractional phase change problem, one-dimensional, one phase, where h, again, is the inverse of the interface. We suppose that this interface is an increasing function. And the model now is given like this. I like this way of the model of the equations, because this way allows us to use Green's identities, for example, that they are not usually combined when you use Caputo derivatives. But what about the model of the mathematical model for this related to this problem when I work with Caputo derivatives? Okay, the problems it's equivalent to the done before, and it's given in these terms. So when I have Caputo derivative, I have an extra term in the equation. Oh, well, I was so sad because it was very difficult to me. I couldn't realize to find an explicit solution to this problem, of course, because of this term, this starting term of the fractional derivative. It was so difficult to me. But this year, a few months ago, Roberto, an Italian friend who studied these terms, sent to me a paper done by Professor Kubica and Katarina Rysewska that, it was very nice to meet them now at the conference, and the good news was that this problem has a solution, and moreover, it has an explicit solution. So you made me so happy, and I'm trying to think about which relation could be to this problem and the another one, and the problem when the solutions started from 0, simply because they are so nice, the solutions in terms of right functions, and I cannot. I want to give them a sense, because when mathematics goes so well, it used to be with physics too. Okay. Okay, so there exist explicit solutions to these problems, but I didn't found it. The last part of the talk is when we consider space fractional Stefan problems. Suppose again that we have a temperature, a one-dimensional phase change problem, which is constant at one phase. And now we suppose that we have a fractional flux given in terms of the spatial variable. We will think that at a position, at a fixed position, the flux is given by a generalized sum of the of the weighted sum, a generalized weighted sum of the flux occurring in the previous position, starting that an initial position, and that is what is given, that will be proportional to our flux. That will be the definition of our flux. If you try to think about it in terms of fractional derivatives, it could be like a Caputo's flux. So with the same reasoning, using the continuity equation and Rankine-Hugona conditions and the interface, we get this fractional Stefan problem for a fractional space flux. What do we know about this problem? Okay, it has been already studied by Professor Rysewska, and our inspiration from Professor Rysewska and ours too, again, has been Professor Boller, who planted it a few years ago. So, Professor Rysewska has proved that if the interface started from a positive number and you consider an initial condition, also she had another condition here, there exists a solution. This problem is different because we started from zero, but it's different, but it's similar. So our approach was to consider a similarity method with a similarity variable given by this variable zeta, which is x over t of a power of 1 over 1 plus alpha. If we consider this similarity variable, we can transform the fractional spatial equation into this fractional ordinary equation, which in terms, if you look like the first properties that we talk about the fractional Caputo derivative and the Riemann-Liouville derivative, this is related to the Riemann-Liouville derivative if I make this substitution. So we could transform the Caputo derivative into a Riemann-Liouville ordinary derivative of order alpha between 0 and 1, where now, which is easier to solve. Of course, these solutions are given in terms, and this takes me from the first part of the talk, this solution, to trying to obtain a solution to that equation with Riemann-Liouville derivative, we will use the result given by Kilbas, that the Riemann-Liouville derivative of a power of the three-parametric Mittag-Leffler function can be written like this. So, thanks to Kilbas, we know which is the function sigma in terms of the three-parametric Mittag-Leffler function. Look, the only parameter here they are three, but two are both in terms of alpha, which is our order of derivation. We don't have another one. And then if I have sigma, then I can recover theta. And if I recover theta, then I will recover a general solution, which is here. Okay, a ver. Then a general solution in terms of three-parametric Mittag-Leffler function of a special one-dimensional space fractional diffusion equation is given in these terms, a similarity solution is general. Then plane with these constants in the other equations, we can state that this solution here is an explicit solution of the autosimilar variable x over t to the power 1 plus alpha over 1 plus alpha, where the interface is a power of 1 plus alpha, and the parameter that characterizes it is a solution to a determined equation h alpha equals 6, where this equation is again in terms of the three-parametric Mittag-Leffler function. So which is difficult here is to treat with this kind of equations. But we think we done it. We joined to Professor Tarsia and Lucas Venturato, who are my partners here at Rosario. And well, this is the last solution, explicit solution, that I would like to talk about. Thank you very much for all, and see you the next time. Goodbye.